So I want to introduce myself quickly. The only thing I'm doing today is the intro before handing it off to our moderator and speakers. But I'm the new director of community at the Hertz Foundation. I started last October. I've been talking to a lot of fellows, both in school and out of school, and I've had a really great time hearing about your experiences. I know that one of the key differentiators of our community is the diverse and wide-ranging fields that we represent. And that actually corresponds to a lot of really cool opportunities potentially outside of your field as you go to look to your career. So I think that this event really exemplifies that. Opportunities to learn about paths maybe that you haven't thought about, network with some really cool Intel staff, and think about professional development that you might want to pursue whatever career stage you're at right now. If you're a fellow who's already embarked on your career and you're working at a company that might want to get in touch with us, please do reach out to us at info@hertzfoundation.org. I will throw that in the chat to let us know what you might be thinking about. We are always really excited to connect the Hertz Fellows of all ages to amazing engagement opportunities like today's info session. As a very last announcement before passing this on, I want to make sure that everybody on the call, all our Hertz Fellows, have our summer workshop marked on their calendars. July 14th to 17th, registration opens next week. Get excited. So now my final task is to introduce our speakers. So I will tell you about first, Derek Hasseltine, who will serve as moderator today. He's the director of the Hertz Fellowship Program and a wonderful colleague of mine at the foundation. Then we have Gil Vandentop. Hi, Gil. Director of Corporate University Research at Intel Labs. His team manages Intel's university research investments for internal technology and business customers. He completed his PhD in physical chemistry at Berkeley and his bachelor's in honors chemistry at the University of Alberta. Lisa Smith is up next. Hi, Lisa. Diverse Higher Education Program Office Manager at Intel Labs. She manages the strategy for enhancing the education experience for underrepresented minorities at the college and or university level. She has BSEET in engineering from DeVry University and an MBA from Keller Graduate School of Management. And then Gabby Cruz Thompson is our third speaker, the Director of University Research and Collaboration at Intel Labs, responsible for defining the future of computing and communications technologies. She earned a master's in materials engineering from Arizona State University and a chemical engineering degree from the University of Costa Rica. I like the wide range of degrees we have just in those first three speakers. And then our fourth introduction is for Greg Taylor. Hi, Greg, a Hertz Fellow and consultant on analog mixed signal circuit design and systems on chip, also an Intel Fellow and winner of several Intel Achievement Awards. He was responsible for the development of analog mixed signal circuits in a variety of roles throughout his 24-year tenure at Intel Corporation. And with that, I will turn it over to Derek and these four great speakers for the discussion. Thank you all for being here and for your attention and participation.
Great, thank you so much, Anne, for the opening remarks and kicking off today's session. We are, as Anne said, just incredibly fortunate to have such great representation and leadership from Intel's leadership team. So I'm going to keep my moderation really short here in the beginning and turn it over to Gabby to really drive the train in introducing Intel Labs, as well as her colleagues, and then we'll have open Q&A. So Gabby, the floor is yours.
Thank you very much for that introduction. And so just to make sure that we open this as a dialogue, we do have slides. I was asked to do the least number of slides possible because we want more to have a conversation and tell you a little bit about the work that we do and our lives at Intel and you know the careers that we've had at Intel and then what opportunities we see that are opening up. But I think very first important point to make is, you know, who is Intel and what we're here to do. We have been changing our corporate strategy significantly in the last 12 months. We've welcomed Pat Gelsinger back into Intel. He worked at Intel for many, many years, and now he's back as our CEO. And that has changed almost everything in what we do and how we approach a lot of engagements in the last 12 months in so many fronts that hopefully through the presentation, I'll be able to share a little bit of that. Our purpose didn't change with Pat. Our purpose continued to be the same: create a world-changing technology that enriches the lives of everyone on Earth. And this had been our mission for so many years. When Pat arrived in the corporation, he decided there's really no change in the purpose. Um, but he has been very vocal about making sure that we Intel support our customers in this new digital, intelligent, connected device world. So we see and we expect digital devices to be in everything, and so he wants to make sure that we are impacting and we're improving the lives of everybody in every digital aspect or every device that people come into contact, and the devices that we haven't yet released and the devices that we have not yet even created. I think what has been very clear in the last 12 months is Pat wants us to innovate with boldness. And that really simply means we have to be very creative and take risks in the way that we innovate. And that's the job that we foster in our day-to-day life here, Gil, myself, and Lisa. Because we're always working with academics, we are working with researchers around the world, and we need to make sure that we get really different ideas, really bold ideas brought into Intel. Corporations typically have a set of strategies, and it's difficult to make changes. And with the group of researchers that we have at Intel, which is about 1,000 people across all of Intel fundamental researchers, we need to drive different points of view and explore different areas that perhaps business groups would consider very risky propositions. We want to lead in every product category. You will see, hopefully you're noticing in information that comes out from the news about Intel. Last week, for example, we had our investors meeting. So once a year, Intel executives meet with the investors, the stockholders, and answer questions about what they expect to see in the future of the company. And I think in many of those announcements last week, you saw a different stance on the product and the product categories that we have, and the expectation and starting to deliver on executing flawlessly against our roadmap. So I think I'm going to be open and transparent. We've had some mishaps and some delays on technology releases. This is something that we're trying to change. The technology releases continue to be very complex, and we're trying to bend physics to our will, physics and chemistry to our will. But definitely we want to be in a place where what we commit to our customers, what we tell the marketplace that is coming, is actually something that we deliver. And then the other side, in which I think Lisa and Gil and myself, we spent a lot of time, is working on fostering a different and more vibrant community and culture. Being open to new and different people coming into Intel, making sure that there's integration programs, not only the programs, but that reach out to each individual person that we hire, and make sure that the culture that we have is one that accepts all points of view, is part of what we do. So most of the work that the three of us do lie on the first and the last pillar here. But we do this in support of the two central pillars, which is what the market and our customers see. I don't know, Gil, any other comments?
No, I think that's a really good intro. I mean, it is super exciting, right? I think out of all of us, I've been at Intel the longest. And, this is definitely the biggest change that I've seen, in one period of time since the very beginning of my career at Intel, which was in 1990. So it's a ton of fun, and we're right in the middle of it, because a lot of it does rely on university programs and university investments. So yeah, keep it going, Gabby.
All right. So where we are in the world, this is as you can see here at the bottom, something that was created exactly a year ago, and it's definitely not accurate anymore. But I'm waiting, and I'm sure very soon I'm going to get a new slide on this with a few more places in the world. And so I'll talk about what has been there and what is recently announced and what's coming. So we have our core research teams located here in Hillsboro, Oregon. I am in Oregon. I am 3 miles away from the technology center of the universe, and then the research labs are only 4 miles away from my house. I live pretty close to Intel. We have our technology development team, which creates the manufacturing process for the next generation. They are here in Oregon. There are thousands and thousands of people that are creating technology that will be in products' hands and customers' hands 3-10 years from now. There is a huge number of folks with PhD degrees that work in that facility. And it's said that we have more PhDs per square inch in here in this buildings in Oregon than some of the Oregon universities, because we do hire so many folks with high level of degrees, masters and PhDs, and even some postdocs. So technology development for fab manufacturing is done here in Oregon. Product design, product creation is also done here in Oregon, and it's all near Hillsboro, which is a suburb of Portland, Oregon. We then have our Chandler facilities, which are mainly 2 things: our high volume manufacturing of fabs, our silicon manufacturing. We have 3 fabs there, and we just announced 2 new fabs that are being built right now. The groundbreaking ceremony was 6 months ago. So we are planning to hire about 3,000 engineers and technicians in the next 3 to 5 years in these facilities in Chandler, besides the hiring that we normally do for our operations of the factory. And in Arizona, we also have technology development of assembly test. Our packaging facility, the future of how we package silicon, is all dream up in our Chandler facilities. So again, we have another group of heavy PhD postdoc and research and technology development folks there in Arizona. It's in total number of employees is a little bit smaller than Oregon, but it's definitely growing to probably be as sizable as the presence in Oregon. Rio Rancho, we have fab manufacturing there. We also have testing in Rio Rancho, New Mexico. Relative size of the site is relatively small compared to Hillsboro and Chandler, but still we have a vibrant group of folks there doing some high volume manufacturing and some testing as well. We have assembly test, and this is kind of the high volume manufacturing of packaging. So it goes from Chandler, the development portion, into actual high volume manufacturing in Belen, Costa Rica. And that's where Intel hired me 24 years ago. We are doing manufacturing there. There's also a little bit of design. There is also finance and human resources folks there. We have about 3,000 employees in Costa Rica today. We have Ireland is the other powerhouse of high volume manufacturing for silicon, for fabs, and that's why it's in blue. It's our wafer fab productions, and Ireland continues to grow. We continue to build and increase our capabilities in Ireland. And then sister to Ireland is our site in Israel, where we also have fab manufacturing activities. So the development happens in Oregon, and the high volume manufacturing happens in Chandler, happens in Ireland, and happens in Israel. And then we have Kulim in Malaysia, we have Chengdu, and we have Vietnam. And those are all assembly test high volume manufacturing plants, similar to the one in Costa Rica. And then we have fab manufacturing in Dalian, and some of the fab manufacturing in Dalian is being sold off because it was mostly memory fab, and that's a business that is being segregated from Intel, is being sold off to a different company. So this is sort of the world as it's been for factories at Intel. But then we recently announced, about a month ago, we announced new 2 factories in Ohio. And this is going to be brand new, 2 new factories. So we announced 2 new factories in Arizona, and then we are announcing 2 new factories in Ohio. So the silicon manufacturing is really significantly increasing for Intel. These factories are going to take 3 years, 4 years to get constructed. And so in total, we are planning to hire 6,000 more people to operate these new factories. And then our CEO has announced that there are some operations expansions going on in Europe. And then we are waiting to hear the details of that. But that's why I say this page as it is about to change. I mean, there's already some announcements that have been made, and there's some announcements that are coming. So an exciting place to be today, what Gil was referring to, because we are significantly expanding and increasing the amount of manufacturing that we do around the world. So any questions regarding our manufacturing footprint? Lisa, any other comments? Something I missed?
No, I think we'll get to the point where we kind of share a little bit of where you can see yourself with the discipline and experience that you have and the research that you're working on. We need a plethora of that across a lot of these different areas and sites. So we'll get to that point where we kind of share a little bit more of, you know, how you can bring that skill set to the table to help enable the semiconductor industry in a profound way.
All right. And then I talked about some of our sites in the US, but I didn't talk about all of them. Our headquarters are still where our central offices are in Santa Clara, California. We have a lot of design folks in Santa Clara, a lot of product design teams there. We have IT and design also going on in Folsom, California. So if you're thinking, oh, I would like to live in California, well, there's still a lot of jobs that Intel has in California. And then we have a design center in Austin, a design center in Fort Collins, and a design center in Hudson. So those are places where Intel has operations, kind of the main centers of operations in the US. We are opening jobs also in Georgia. So I think as we refresh the slides, you will see that there's going to be also some light blue pop out also in Georgia. And depending on the job that you might be interested at Intel, you might be working from any one of these locations, because we are becoming more flexible with exactly where physically we are all located. So if there's no questions about kind of Intel at large, I would like to jump into Intel Labs and the research that we do at Intel Labs. Can I jump in there? Questions? All right, I see smiles. So at Intel Labs and at Components Research, which are the 2 organizations that do the fundamental research that is required to put up our products, we have these areas of research thrusts. First, security and privacy, ever more important to have secure products and to make sure that data is not leaked and that privacy is protected for the users. We are doing a lot of research on emerging workloads. We are exploring new ideas in different AI algorithms and AI structures. We are also thinking about new ways of creating software. We work on novel sensing technologies, new compute models, and advanced memory and storage programs, as well as the connectivity and the next G, right? 5G is being deployed today. There is almost no more research to do in 5G. our teams are moving on to the next generation of communications, which is still being defined and probably might be called 6G. I think even the title of 6G is not even confirmed yet, but that's what the teams are starting to work on. And then a big chunk, a small part in the slide here, but a big chunk of the work that that we do and that we enable is advancing manufacturing processes for both the silicon fabs as well as the assembly and test packaging operations of Intel. So these are the key thrusts of research. To give you a little bit of more of a flavor of exactly what this means, we have this slide with some of the projects that we're funding with academics today, and some of the projects that you might hear about us publishing information. So Neuromorphic and quantum computing are two very significant programs that we have in place, and these are both trying to create new compute models, new architectures, different ways of doing computing. We are working on how could machines program themselves. So trying to create programmable machines or machine programming. These are some of the academic engagements that we're starting. And then I talked about 6G, but we're also thinking of different ways of improving connectivity within the compute system. And so we're trying to integrate photonics everywhere in the compute architecture system as possible. Gil, any comments you want to make here on some of our core programs? I know you don't like that the advanced manufacturing is so small in the bottom.
Yeah, well, that's true. You know, my background's in chemistry, and so everything to do with advanced lithography, everything to do with novel materials. I mean, it's a huge space. So I'm not sure what all of your backgrounds are, but in the labs, the upper space tends to be exaggerated compared to the bottom box there. So I always like to point that out. Thanks, Gabby.
Mm-hmm.
And I think
Right.
the other thing, Gabby, in this is that, as you can see, for those who may be in the AI space, whether you're in deep learning, machine learning, just all across the AI or data analytics, you can see throughout all of these key areas that we're focused on, there's a little bit of everything in these buckets, because it does take difference in thought, difference in expertise to come to the table to, one, identify a solution to a problem we have now and that we're going to grow into in the future as evolution of technology grows, but also ensuring that we are taking in key components so that the technology can be anything from the edge devices all the way up through to the cloud. And so think of it in that sense. We don't just have a department for just AI. It's embedded and woven through everything that we do.
I guess, Gabby, I'd say one thing more around around the excitement of working at Intel right at this time and advanced manufacturing leadership. I mean, people can see, in the news what the plans are, what the government's talking about in terms of additional investments and the investments that industry is planning on making around domestic manufacturing, right? And so that's one of the things that keeps me going to work every day is the importance of the mission in terms of national security, economic viability and supply chain integrity and all of those things. Intel really feels a responsibility for enabling a lot of that. And, as an employee, we're part of making that happen. So that's another inspiration for working at Intel today, I would say.
Sorry, my mouse has a mind of his own today. It took me a minute to get to the mute button. So before I move to anything else, you've heard the tone, Gil, Lisa, myself. We've been at Intel for a while, but I want to bring Greg into the conversation now. Greg, you worked at Intel Labs. You saw a different slide probably in your days in the labs, but then you're reading this white boxes, and some of them I'm sure are not news to you.
I mean, some of these are areas that were significant when I was there. I mean, what the security lab for a while actually reported to me. So I've worked with many of these areas. And the fact is, when you're doing these significant things, it takes a while. I remember some of the early discussions, Gil had mentioned Yusuf El-Mansi earlier, in the 90s when there were discussions of, originally it was called X-ray lithography and then extreme ultraviolet. That technology took almost 30 years before it became real. But now everything is depending on it. And so, yes, there is continuity in what happens here. There are new things, there are new elements in some of the areas which are important, but also the labs are working on things that take a while before they really see the light of day and become, widespread technologies.
Yeah, thank you. Thank you for that comment. That is very true. And so something that I mentioned in a few slides, I've sprinkled it all over, but I want to make sure to make a point is we are exploring boundaries in trying to innovate, not just by ourselves, but working with academics. It is the central job that we have, making sure that we're reaching out to academia and learning as much as possible from all the work that is being done at universities and all of the fundamental research that is done out in academia, and then partnering with governments. Gil was mentioning how exciting it is today to come to work and to dream up possibilities of expansion of education, STEM education. And how we're talking about workforce development for the United States and the gap in employees that we see coming up, that we need to make sure that both academics and governments have the necessary funds and the necessary open doors to include more people and to increase the number of engineers and technical professionals that are educated. And then we do these things also in concert in consortium with other companies. And so companies that in the marketplace might be our competitors, in the research arena, they're our collaborators. We're collaborating with them. We're trying to drive the state of the art for the industry. It's not just for the benefit of Intel, but it's for the benefit of the industry at large, and making sure that that technology continues to progress and continues to get better every day. So an example of a collaboration with companies and with government is the recently announced National Science Foundation AI Research Institutes. This is one of the biggest programs that NSF has in computer and science information. Today, they've done 2 level of awards, 2020 and 2021. They've announced $220 million in investments, and you can see that universities almost in all the states have been getting funding to do research in AI. You can see here and highlighted in blue 2 specific institutes that Intel is co-funding with the National Science Foundation. One, TILOS in UC San Diego, and then the other one, AI Institute for Optimizations out of Georgia Tech. But then it's not just those 2 universities, but there is connections to other universities in the map here. And we, Intel, we're not the only company co-funding this efforts. There is also the USDA department, and there is also Amazon, and there is also Accenture. So again, it's kind of a show of how we're trying to build this together and not going at it separately. I don't know, Gil, if you want to mention something about SRC. I didn't put the SRC picture here, but if you want to mention how we work with SRC.
Yeah, I would like to. I mean, that's, the opportunity to continue to work with universities throughout your whole career. That's one of the things I value about working at Intel. And so one of the first things when I got my job in Oregon, my first boss is like, oh, I want you to be a mentor for an SRC project that, it was at Champaign, Urbana, a guy working on plasma etch. And I was like, a mentor? It's like, I just graduated, why would I be a mentor to somebody who's at the same stage? And then he explained to me, you're not you're not expected to, help them do their research, but you're expected to help them understand what the company's like, right? What the applications of their work is and that sort of thing. So that was my first experience. And I think it was in my first or second year. And so he was an SRC sponsored student. The SRC is a Semiconductor Research Corporation. And so I continued to have these relationships with students. Actually, that particular student, both he and his wife ended up in the same group as me in Oregon. And, we've been friends ever since. But so, different types of those opportunities. And then eventually, just a few years ago, like 7 years ago, I went on assignment at the Semiconductor Research Corporation, and I led a large program where many companies would pool their money. It's kind of one of the ways that we do our longer term research, pool our money, select some large centers in partnership with DARPA, and then run a 5-year program looking at pretty far out research. And so I did that for 5 years, and that was the job I had right before I took on the university program. And now, we continue to do a lot of work through SRC, including a lot of workforce development investments. Back to you, Gabby. Any questions on SRC? Okay.
All right. So other programs that we fund besides just the funding of research with universities, we encourage universities to use Intel technology in the classroom. So we sponsor a curriculum that gets created so that all our new products and our new tools are available for students to learn and learn to use them as part of their education. We have a group of selected universities that we consider our strategic partners, our strategic collaborators. We provide recognition and some funding for faculty. So one of our awards is for new faculty. And I want to mention this because if some of you are thinking to stay in academia and become professors, one day we would love to sponsor your first research years. And so for that, we have something called the Rising Start Award. And we give these awards once a year. They're announced normally in September timeframe. And that's how we start to collaborate with new faculty, with new professors. And so if you're thinking, oh, maybe I'll be a postdoc and then I'll move on to work in academia, don't forget about us. We're not here just to try to invite you to be Intel employees. We're also inviting you to be a collaborator, to be part of our research network. We offer a compute environment, a compute in the cloud with some prototype hardware that we make available only to researchers. Our neuromorphic computing prototype is out and available. It's being used today by over 200 research teams around the world. It's not a product. We don't sell it. We only make it available for researchers and for people that are willing to play around with it and use that prototype. So that's one example of something that we have in our academic compute environment. And then we are also sponsoring and donating services from our Foundry team, from our design team. We are not sharing this with a large number of students, but hopefully in the future we will be sharing it with more, which is the ability to use Intel Design Kit to prototype and actually build a silicon chip and design on Intel's Foundry. So this is a new service that we are offering. We have been offering it to a few universities in the last few years, and then slowly you will hear probably more from us because we're trying to expand the reach and the number of students that have access to it. Gil, is there anything you want to mention here?
No, you covered it.
All right. And then Lisa, do you want to share this slide?
Yeah, as Intel evolves and we've built technology, I know when I started with Intel, it'd be now 25 years in another month. I knew Intel's brand, but I didn't necessarily know Intel's culture and where they were trying to drive their technology. All I knew about was a lot in the compute space as it relates to computers, big enterprise systems, that kind of thing. If you think about it and just take a step back, where is the semiconductor technology currently being deployed into from an industry-wide technology perspective? If you can imagine every ATM machine, even a toaster, a TV, your refrigerator, your washer and dryer, there's so many devices that require semiconductor technology. And then think about the individuals that are building it from a design all the way to mass manufacturing. If the technology in which Intel is providing to the industry and community globally is diverse in nature and where it's being deployed, we need to ensure as an Intel family that we have a diverse workforce to meet that demand and need. Because the need grows and is different based on the usage of that technology. And so when we look at this, we look at it as what we call as our RISE strategy. We want to be responsible in the technology that we're deploying into the industry globally. From a, revolutionizing, how technology is being improved and being leveraged to improve everyone's health and safety around the world, but also making sure that we're being intently focused on ensuring inclusion, making the technology fully inclusive and expanding it to digital readiness. That's so many ways, right? When you think about countries that may not have the Wi-Fi infrastructure, when there's a disaster around the world, how do we engage as a responsible company to lean in with that community to help ensure that their rebuild is incorporating these aspects and equity across the technology so people can have access to it. And then thinking about the sustainability of it all. When we think about building a new factory, we're thinking about what is the sustainability as it relates to the energy efficiency of it. So think about if you're in electronics or you're thinking about power consumption, we're thinking about that too at the facility level. How do we leverage that power in a way that we can rejuvenate that over and over again? I think one of the pictures here kind of shows some of our solar panels in our factories that are near our factories, our facility buildings, but also enabling that. Enabling and unleashing is what we used to call it, our employees to be the best and to bring their authentic selves to the table so that we can do this collectively as a community body to really move the needle and making sure that we're deploying technology in a sociable but equitable but also intentional way. And so that's what this represents. Our RISE strategy is really about employing difference of thought, difference of experiences, education backgrounds, communities to the table so that we can collectively build something that is so inherently needed, but also adopted in our communities worldwide. If you go to the next one, I can kind of share with you a little bit of when we talk about jobs, it's again, when I started with Intel, I wish someone would have taken me through a map of how can I leverage my Bachelor's of Science of Electrical Engineering Technology degree at Intel. I've done everything from working in manufacturing, starting my career in lithography. So understanding, we call that the heartbeat of our fabrication process, knowing every layer, every transistor that we build, it really starts in the heart of that, particular part of the fabrication process. But also working in assembly test and development as well throughout my career, ending up in commodity management, ending up evolving from there to working on training across assembly test, fabrication, and across the company, and ensuring that new people coming into the company and onboarding were educated on how does Intel run, but also how to be safe in the work that they needed to perform for our company. And then evolving into doing recruiting for Intel into other organizations and management of our ecosystem in order for us to get to exascale with our technology. And now I'm full circle and working on diverse higher education. So working on with academia and you guys to show you that there is a path for you. What you're learning today and what you've experienced today could map to any of the roles that are listed on here. You can be, let's just say you got your master's, and I'm kind of making this up based on the group that's here. So Charles and Charles, I'll take you and I'll just say you guys are electrical engineers at heart. You're learning a lot about power consumption at the circuitry level, but you also know and understand medium power, where you can work in our facilities. We have huge facilities around the world, and we need to understand how are we leveraging power to its maximum capacity, right? How is it being deployed to our factories to keep up with that need? But in the event we have a disaster, how do we recover quickly? so that what we're doing in order to enable technology for society keeps running as a well-oiled machine versus being down for long periods of time. But you can also work on our circuit design. You understand, how do we bring power to the different components of a board or a big system like a data center? Those type of nuances and experiences that you're forming now in your research, in the work that you're doing at school and academia, could be playing a role in hardware, software, interconnects, embedded devices, Internet of Things, data analytics, high performance computing, cloud computing, whether it's on the actual system itself or hybrid into the cloud or totally into the cloud, into an enterprise-wide solution. It's a gamut. So think of it as you possess a skill set. You're bringing this experience and skill set to the table. We have what I call buffet of opportunities at Intel, whether in an internship position. An internship, I'm going to use that a little loosely to say whether you stay here 3 months or you stay here 9 months, as long as you don't stay here a full year, you're considered an intern. And that's really how we hold our internship opportunities, is that it's a wide range of opportunities. You can do part-time while you're still in school during the spring or fall, and you can do full-time over the summer. It just kind of depends on the group and what type of work, body of work that the manager has. But you could also see yourself from a full-time perspective in the company, working your career from, coming in as a college grad into one of our technical areas, but growing your career into to Greg or Gil's or Gabby's level of expertise is really towards that technical path at Intel when you're talking about going from principal engineer into fellow. And so there's all types of paths, and Intel has training and sponsors and mentors along the way to help show you that blueprint, is what we call it, for your career, if you so choose, because it is a self opt-in if that's an area that you want to grow in. We're going to provide this slide to you so that you can click on all of these links that are presented here. Just know when you click on those links, it's going to give you a plethora of job opportunities that are embedded in it, whether it's manufacturing and facilities or if it's in our hardware and software. All these areas are open right now, and we're hiring by the thousands. I know you heard Gabby talk about all the different sites and areas that we have. There's even right now with our interns, they're working remotely. If you're not embedded in one of our factories, which is important to us because we have to keep our factories running to produce the technology, then you're working as a remote intern for Intel and one of our other business groups that are listed here as well. And if you understand technology, you can sell our technology to our customers. And that's the beauty of it, is working and engaging with customers, trying to help them solve problems that they have today on whether it's them taking the components of their technology, embedding ours, and then selling a hard product, or whether it's really selling a solution. That's really working with a lot of those big enterprise companies that may be looking at, how do I create another data center in this particular region of the world in a way that's energy efficient, that runs on, instead of it being air cool, it's running on some type of liquid cool system. Those type of solutions require us to have engineers at the table to help solve those problems. And so I'm hoping we gave you a bit of a picture of, it's not just a brand. It's not just, hey, we're working on computer chips. It really is solving some big problems in a way that is designing it, thinking about it, designing it on a small scale, and then mass producing it for the bigger global community in which we serve. And so I just want to step back and say, I know we're excited. We've been around quite some time at Intel, but we really want to open this up for you to be able to ask questions. Because I wish I had this type of platform and environment to ask that before I joined Intel. It might have helped me in navigating a lot of areas that I've been able to drive my career in, but we're hoping that you would be open to ask questions so that we can help you in navigating what you want ultimately in a career and yourself. So without further ado, I want to open it up to Derek or anyone to ask questions, or if you want to take it from here, Derek.
Sure. Thank you, Lisa. I think that was great. I'm like, wow, so many notes here taken. Just a really great overview of the organization. I think where you're innovating, your current needs, and then just a nice overview of the culture. So I do have a long list of questions here, but I want to give the opportunity to our fellows and offer the floor to them to jump in with any questions. And I think for the benefit of our guest speakers here, if you do have a question, if you just want to quickly introduce yourself and your research area or area of focus, that would be great to bring a little context. So I'll go ahead and open it up to our fellows. Feel free to jump in, unmute yourself, and ask away.
What specifically are the sort of near and medium term plans for memory design? Do you guys know much about that? Or are you personally involved?
That's a good question. I don't think any of us are personally involved in memory design, but we do have a lot of investments at universities in that area. And it's interesting. One of the things that actually kind of frustrates me is we've been investing in, it's called compute in memory, or you can turn the name around, right? But especially for AI applications and energy efficiency, doing some of these large optimizations. And there's a lot of different ideas around compute in memory, but we've yet to see something that actually has gotten traction in terms of a functional capability that we can sell. I still believe that there's opportunity there, and we do invest quite a bit in that area. What are your thoughts in terms of the new frontiers in memory architecture or development?
Me personally?
Yeah.
So so some of the applications of what I work on now could be in sort of very low dissipation memories and things like that. But the kind of research that I do right now is pretty remote from an industry application, just because it works at low temperatures.
Okay.
Yeah, so I was just curious about what that looks like at Intel, what the research actually is.
I think, Chris, I'm going to throw something in the chat window. Always say, Intel typically has a ton of stuff on our website. I'm not asking you to comb it in its thoroughly because it's a lot of content, but I'm going to throw something that talks about our Optane technology around our memory and storage. So think of it as like non-volatile memory, if that's helpful for you as it relates to your research work, because there may be some connection there in some of the areas that you're looking to grow in, or to maybe understand where the industry may be going and what's our play in that. If this is helpful, I'll throw it in the chat window for you.
I mean, over the years, Intel has done work on multiple non-volatile technologies. I retired 6 years ago, but at the time there were active programs on Optane, but also spin torque-based memories. SRAM has been something that Intel has done throughout. There's been a lot of optimization there. We've used DRAM technologies in some of the graphics products, and there's been device research as well as when I was there, we were doing research on architectures to take advantage of error control technologies to reduce power as opposed to increase resiliency. So it's everything from device architecture through to the logical architecture to get the most out of the devices. Yes, what you're doing, low power may not be something that goes into a commodity item today, may never go into a commodity item, but it still may be of interest, and it may be the concept somehow can be applied.
What actually are the most desirable performance metrics like right now? Like, is the most important thing low power dissipation for a memory technology?
Well, power dissipation is key because with memories, you got a whole bunch of it. And so you really want the power dissipation per cell to be low, but you also care about how robust is it? With silent data corruption type problems going on, you'd like to know how well does it resist cosmic ray influence is the dominant one in DRAMs. And then what do you have to wrap around it in order to make it reliable? So there is no single metric that dominates everything. Power certainly is an important one, but reliability, cost, performance all matter as well. And the other thing is, in different applications, you'll have different mixes of the different requirements.
I know there are some like spin transfer torque and magnetic tunnel junction memories that some companies make. There's this company Everspin that makes those. What is the use case for that? I think there's some language on their website about peripherals or yeah, you probably know more about this than me, so I'm just curious.
Well, I don't know I mean, in terms of use cases, the obvious ones are non-volatile memory, but work at Intel has looked at using it not just as non-volatile storage, but also at using it as a computational element, compute in memory, and then as more localized storage, because although magnetics, we tend to think of them as being non-volatile, it actually depends on, how big is your domain? What's the energy barrier in the device? Is it truly non-volatile, or is it actually volatile because you've shrunk things to such an extent? And so again, usage models vary.
Great, thanks.
Yeah, and Charles, actually currently, I mean, Greg mentioned it, but our biggest investments around spintronics are are for device applications, or for very energy efficient device applications. So we call them MESO devices, magneto-electric spin orbit torque functionality for the switching. We've been working on that for about 20 years, and it's getting close now, so that we've got some actually very specific investments with academics in that space. But yeah, that's the kind of committed investment we have to have for some of these new technologies to really keep working on it to the point where it becomes commercially viable. And then in terms of low temperature stuff, I mean, we've got a pretty active quantum computing program, right? And some of our more recent advances are moving some of the signal processing down closer to the qubit, which means, like, I don't know if you're familiar with that, but it sits in this big dilution refrigerator. And, the further down in the fridge you go, the colder it is. But I mean, the harder it is to integrate, right? So in terms of optimizing the efficiency and also the stability of the quantum computing sort of core functionality, we're building these devices and then bringing them closer to the qubit themselves. And I don't know exactly what memory we use, but I know there's some low temperature memory there. So it'd be interesting maybe to do some homework and let you know what we're doing there. I think it's more conventional memory that still works at low temperatures, but I'm not sure.
I was going to
Great,
add,
thanks.
Charles, our biggest center of research, academic research center for memory is the CRISP Center inside SRC Jump. I put the link. I just said a bunch of things that probably don't mean much to you, but I just put the link there for the CRISP engineering at Virginia. And it's not just Virginia, but it's a group of universities that are developing this for SRC and for everybody in the semiconductor industry.
Yeah, no, I mean, that's interesting history, because it seems like we're at a similar point again, right? Where there's a lot of emphasis on domestic talent development, right? And increasing the number of students that are going for STEM educations, because there's so much of a leadership opportunity and need these days across the country. So it's interesting that that's a similar situation to when Hertz sort of started its contributions. So yeah, thank you for that. And I just noticed that Sarah put a question in the chat. I'm curious how tightly Intel is involved in applications of their technology. Does Intel have research focused specifically on certain applications like healthcare, or is most focus placed on the foundational technology? And do we rely on partners for the application piece? And we do both for sure, Sarah. That probably it's certainly lower. Like when we talk about technology, we talk about the technology stack, where at the bottom it's fundamental materials, and then the device physics all the way up to systems and applications, right? So at the bottom of the stack, we're very focused on the foundational technology because we're using it to build, right? But more upwards in the stack, yeah, we do quite a bit of investment around applications, right? And understanding what emerging applications will be, right? Because for our future business, that's really important. For example, when artificial intelligence or more specific DNN type machine learning really came into vogue, we kind of missed it, right? I mean, we had been interested in it earlier, and then it kind of went quiet, and we kind of missed it, right? And then we're catching up in terms of GPUs and silicon optimized for matrix multiplication, for example. But we don't want that to happen again. So the way we do that is by investing in the applications space for our products, right? To make sure that we have visibility there. So yeah, thank you for the question. That's a good question. Oh, you got another one too.
The second part.
Yeah.
Hey, Gil, I just wanted to say, Sarah, I used to work in our data center group on ecosystem enablement around life science applications. So Amber, Neuron, and there was a couple other life science related applications that we were trying to optimize on Intel architecture. And so that's just one example I threw in there, but I threw in another one around our One API technology. This is a software where you can run on any hardware. And so in that, if you go to that link, it will show you the latest applications that are in life science, everything from breast cancer to genomics, so on and so forth, that is being leveraged using One API, if that's helpful. I assume, Sarah, you're in kind of the life science space world, and so you may know some of these terminologies or apps that's being used. So hopefully that's helpful. Oh, go ahead, Gil, with the next question.
Oh yeah, we had the second piece around global challenges. I mean, that's a pretty open topic, right? It makes me think of a few things. I mean, one of the things that I've been more involved in recently is with SRC, we wrote what's called the Decadal Report, which is sort of a forward-looking document in terms of what the challenges within the industry are. One of the biggest ones is energy, right? If you extrapolate the amount of energy that gets used for computing versus the total world energy production, right? I mean, the extrapolation doesn't work because it looks like it'll cross, right? Of course, it'll never cross, but the rate of increase is not good, and one of the biggest global challenges, right? So we're always trying to make our devices more energy efficient, but you can also argue, I mean, every time we make them more efficient, people just use them more, and the increase in energy continues, right? So we need to look at it a different way, like how can we enable a different type of compute that is not just a linear function in terms of energy per operation. So that's one of the things. Another global challenge is we're building all these big factories, right? And some of the investment that needs to happen is around water usage, recycling, all the sustainability aspects of our factories themselves, and then also the data centers where our products are used and use a lot of this energy. So yes, we do invest significantly in that space. We do research in that space, and I can only see us doing more with these global challenges that we're looking at.
There's also another side to that same problem you mentioned, because this was brought up when I was actually working in Intel Labs about a decade ago, but about 2% of the world's electricity was going into data centers, which I think is still about the same number today. So efficiency has been pretty good. But it was pointed out that about half of the world's electrical energy goes into motors. And motors are not terribly efficient. I mean, if you look at them, they have a performance curve, and if you get everything right, they're very efficient. But on the average, motors across the world are really pretty crappy. And electronics allows people to design motors to be more efficient, but also to use motors more efficiently. So we also need to look at places where we can use electronics to make other problems better, in addition to making sure that we don't screw the world up with the electronics that we have.
Good way to put it. Thanks.
I just want to point out, Nolan I think he's gone. He had a question. He posted it in here, something he's interested in. I think it would be good to just address that now so we have it in the recording for him and other people. I need to head up. Thanks very much for the intro to the labs. I'll be interested to learn more about your materials and quantum research in the future. I'm going to speak to that.
Yeah, I mean, materials research, our materials research is quite varied, right? I mean, if I go back to the last question, I mean, in terms of sustainability, we do research in terms of maybe eliminating materials that we would rather not see as part of our process, and certainly as part of our effluent, for example. That's one big part of the investment. Another big part is new materials, right? As the sort of traditional scaling of Moore's law with, takes us as far as EUV lithography can take us, we still plan on shrinking the transistor, and the way we plan on doing that is with two-dimensional materials, right? So these are materials that are only monolayers thick, but you have to stack them in a certain way that's completely defect-free if you want functional devices to create, a switch that's much more energy efficient than a scaled CMOS device. So we do invest a lot in that type of materials research. Interconnect is a huge challenge area where, as you continue to shrink, you really, you hit these limits of increasing resistivity, but there are certain structures that can enable power delivery or signal connections with low dissipation. So we do that type of fundamental materials research. Actually, that's the job I had before I moved to Semiconductor Research Corporation for a few years. I set up a novel materials group, and we did fundamental synthetic chemistry and this is an area where it's unusual, where we actually had to do the most fundamental work, and then sometimes we would transfer that to universities to maybe expand the space a little bit further, or to companies which start to do some of the scale up, and they wouldn't do the initial work. I mean, quantum research, I mean, we're actually pretty good about updating, publicly what we're doing and where we're going. We want to build a silicon qubit, which everybody else is focused on a different type of qubit, but we think that with our silicon processing expertise, we will be able to scale quantum computing more effectively than any others, if we can, perfect this silicon qubit, which is right now quite a challenge in terms of scaling it to large enough numbers that the computational capability is relevant. But yeah, just keep watching. We'll keep publishing on our progress around quantum computing.
Do you know much specifically about what 2D materials you're working on? Like what the substrates you guys think are most promising are?
Well, I mean, I would say substrates. I don't know if I'd use the word substrate, because sometimes they're freestanding, but the material we're looking at, transitional metal dichalcogenides like tungsten diselenide, molybdenum diselenide, even molybdenum disulfide, and then specific stacking of these materials, only in small areas where the actual switch itself is, right? And yeah, and then they're almost substrate free, right? Because we're trying to keep the interactions at the interfaces to be minimized, especially on the bottom and on the top, and then engineered very specifically in between the separate two-dimensional material layers. I don't know if I'm answering your question. Is that what you were getting at?
That answered my question. Oh, the tungsten selenide, molybdenum selenide. Yeah, that was the answer.
Okay.
Excellent. Do you guys try to do wafer scale growth of TMDs? Does that work?
That's current work right now. So I used to give a talk where I would tease the academics that that we've been working on 2D materials for a long time, and we started by digging them up out of the ground, right? And I call it exfolio mania. It's like, okay, yeah, you use Scotch tape to peel them out of geological samples, and it's like, well, you can do some interesting device work, but it's a long ways from manufacturing devices, right? And then we moved to the tube furnace, and so that was the thing. That's not very scalable either, but at least it's better than digging them out of the ground, right? And then now finally we're using atomic layer deposition and doing a very controlled layer by layer growth of these materials, and we've finally convinced some tool manufacturers to make some of these early investments to build some equipment that's relevant. And now we're working in partnership with the equipment manufacturers to try to actually scaling to a full-size wafer. And maybe we're just doing patches of atomic layer deposition of these 2D materials, but you still have to have uniformity over this 300 millimeter wafer. But yeah, those are some of our sort of more near-term risky research investments that are ongoing right now.
Great, thanks.
I love that stuff. You can probably tell I get excited when I start talking about 2D material deposition.
I saw our other Charles unmute for a second there. I didn't know if you had a
Yes,
question,
hello.
Charles.
Yes, I do have a question. Yeah, so super interesting talk and stuff. I'm an AI scientist, so I'm super interested in well, for example, if we're talking about sort of research stuff, where y'all are kind of going with the neuromorphic computing and that kind of area of research, whether, and the answer could be both, whether you're going with the kind of algorithmic approach, where you're sort of trying to figure out new ways to exploit stuff like sparsity and how you train neural networks, or whether you're coming from more of a kind of hardware approach, where you're trying to do things like gradient descent in maybe sort of, I guess, analog ways, or in interesting physical ways, stuff like photonics. Do you see one of those as being your main push? And is there something specific in that area that is the big next thing that y'all are working on?
Yeah, I mean, the answer is both. Definitely, we're working on algorithmic improvements, right? And I mean, we have to do both because we have to hedge our bets, right? We want to be able to sort of lead the application space with sort of the traditional types of compute platforms that are used for neuromorphic computing. But at the same time, we have this whole separate group led by Mike Davies, who's building, the Loihi 2, larger and larger scale ups of a specific type of spiking algorithms. Well, and it's hardware which enable these spiking algorithms, right? And so we're doing both of those things, right? We're hoping actually that the hardware solution is going to be our hardware solution, because that's how we make a lot of money, right? But we're doing both, right? And the neuromorphic Loihi platform is interesting. I went to a conference the other day. I mean, I was kind of it's not my area of expertise, but I was really encouraged by how many people were talking about the Loihi platform and things that they're doing in terms of experimenting on that platform. So I'm encouraged that it's got some legs, but yeah, we will continue to invest along both of those fronts.
I think if you're doing any sort of research today on neuromorphic topics and your professor is not part of our community, we are still open to providing prototyping access to the hardware. Loihi 2 is our new hardware, so it's the second revision of our design. It just got released about, I don't know, in the fall last year, so it's pretty new out there. We are providing some funding to some of the PIs, but then there is, I mean, it's really small, the funding that we're providing. It's many, many more PIs that are actually, students and PIs that are actually accessing our Loihi prototype in the cloud. And in some cases, we're even providing hardware to researchers. And our Lava software, which is the companion to Loihi 2. So we have now a software instantiation that hopefully will help people to experiment with algorithms. And we're advancing everything. We're advancing the hardware, we're advancing the software that we call Lava, and then we're learning from all the potential applications that researchers are experimenting with.
Very
And
interesting.
I hope you caught that nuance of, when we are evolving technology, we think of it from cradle to grave. And so, that expertise that you may be bringing to the table around neuromorphic computing, you're going to learn a lot about the hardware, software, and interconnects between the two, how it's being leveraged. And so, we call it, you're going to evolve into one heck of a great validation engineer eventually, because you'll understand the nuances of what it takes to develop that technology, but also to sustain it in the emerging markets that it's going to be deployed into. And so, Greg, I'm sure you can attest to this on some of the things that you've learned that may not be your current skill set, but that you'll evolve into understanding how you're impacting other aspects of that technology and connections to it.
No, actually, I thought that was one of the valuable aspects to Intel was I actually spent most of my career not in Intel labs. I spent 6 years in Intel labs, but I was able to work with people in packaging, design, process development, reliability, test. And it's amazing how often I would talk to someone over there somewhere, not my responsibility, and find they're pounding their head on the wall dealing with something. And I would realize it's really easy for me to make that problem go away in my domain so they don't have to deal with it over there. But if you never talk to them, you don't know they're doing it. And so there is actually a lot of value in being able to talk across the whole problem from cradle to grave, as you say.
Yeah. Thanks. And I threw something in there too, Gil, as you were talking. Again, I am like a researcher, like nobody else business, because Intel has so much meaningful content on our website when we talk about the different technologies that, again, I don't want, you're asking a specific question, but that might be a link to some additional aspects of just that technology, but also to connect you to other things when you click on that link. So Charles, hopefully that'll help you as well.
Absolutely, thank you. I think that was really interesting that y'all were kind of speaking to kind of this cradle to grave creation of these things. Would you see that as like one of the main benefits of being in a large organization as opposed to a small organization, or maybe working kind of independently as a researcher? Is that ability to kind of connect with other people along the line, maybe who are not exactly what you're doing? Do you see that as like one of the cool parts of being in a larger organization as opposed to a smaller one?
I think that nowadays it's very attractive to work in different startups, right? And go from startup to startup to startup. And I'm sure that has very significant financial benefits to people. And some people I know have loved it from a personal financial perspective. But us that have been spending time in large corporations, our stories are rarely told outside because we're kind of private, and then a lot of the work that we do is confidential. But we get to change our jobs and our careers as much as we want. And you get to work in the front, in the back, in the side, in the customer, and the reach could be really, really large. Take it from me, I started in Costa Rica in one of the assembly test factories. Then I moved to work in technology development and in quality and reliability. And my job for many years was to walk the factories in Asia of all our suppliers and find out what could go wrong. So there's not, the scale and the largeness of Intel gave me the ability to go to all kinds of different manufacturing production lines and learned a lot about many different manufacturing processes. I love that. And then at some point, I ended up doing audits for working conditions and how the workers were being treated at those factories. That was fascinating to me, right? And I'm an engineer and I love technology and I love the manufacturing piece, but one day somebody asked me, Gabby, what do you ever talk to the workers? Do you ever ask them about their living conditions? You know, many of them live in dorms. How are those dorms looking? And so I spent 3 years of fascinating work digging into, you know, working conditions, sustainability, ethics, and managing the supply chain. And now I work in Intel and Intel labs and research and academia. It's a completely different career if you think about it that way. But this large companies allow you that movement, and we actually, as managers, we encourage people to move around, because a person that brings a diverse experience will have different ways of attacking a problem. And so I think that all of us here have been in many different jobs at Intel, and could tell very different stories. And somehow, you know, today we try to solve problems, and we take back from an experience from somewhere very differently.
Yeah, that's a good way to put it. And even in our current job, since the company is changing so much, even within my job now, I mean, everything has changed so much, right? So now, you know, our focus is becoming a foundry, right? So, you know, we're not just doing research to push Moore's law ahead. We need to, you know, anticipate all these other customers, right? And what the fabs need to have, you know, inside the four walls in terms of technology to address the needs of these new customers. So even without changing the job, you know, 6 years is the longest I think I've ever been in the same job at Intel. But it's changed on me, right? So I don't have to go anywhere.
Yeah.
Pretty cool. That's really interesting. Yeah, I'm always very impressed by the hardware people, because making physics actually do things is so extraordinarily hard. Yeah.
I might just add at this point, I'm glad you asked the question earlier, Gil, of our fellows, you know, what do they think would interest Intel in our Hertz Fellows, which is exactly what I was approaching you about. And I think they're humble. That's one thing they may not say about themselves, but they're also right in the middle of their research and everything they're doing. But I would say maybe 3 things that they may not say themselves. First, that they're very, very bright, and our selection process, and Derek has told you a lot about that, sets them apart. And they're not going to tell you that because they're too humble to say that. So I will on their behalf. 2, it's this cross functionality, this working across different fields that I think really appeals to them, that we really encourage, that I just want to say out loud is something that Intel offers in a very large place. You saw the map of where they are in the world. So there's that kind of opportunity. And 3rd, it's this commitment to national security. I mean, they're in-school fellows. They haven't, you know, they're still developing, and they may not think about that very much. They each agreed to that moral commitment that the Hertz Fellowship obligates them to. And it's another thing that brings that we share, that the Hertz Foundation, our fellows, and Intel shares, wanting to solve national problems. It's security. So it's less about defense than it used to be, but there are many types of problems that we're dealing with today. And many of our fellows are tackling those. And I think that appeals to them. They really, from everything we've heard, Derek, and when I meet with fellows, it's that they care about the state of the country, the security, the economy. They're working in fields where it's impacted by, or they're trying to address those problems. And I think that appeals to our young fellows, whether they're tackling those things today. We believe they will, which is a reason that we select them. And so they may not be able to say that yet because they don't quite know where they're headed, but we select them because we know those are the kinds of things they will tackle, want to tackle, and will have an impact in. And Derek, I don't know if you or Ann would like to add to that, but that's certainly what excites me about working here, and it's why I wanted to bring all of us together.
Yeah, that's well said, Carla. I mean, it underlines why, like, right now is such a great time And if you look at, the alignment of, what the values that you express, the Hertz Foundation has that are, that come out of these fellows as well. And that's Intel is working more closely with government agencies, with companies that build devices for government agencies, right? For all sorts of, national security and economic imperatives, I guess I would call them, right? And the world's a different place than it was a few years ago, and Intel is committed to being part of the solution. And so it sounds like there's a real resonance there in terms of forward-looking goals and priorities. So, thank you.
Yeah,